Welcome to AI Paper Slop. Today we're jumping right into a paper from researchers at Tencent, published on July 14, 2026. It's called Harness Handbook, Making Evolving Agent Harnesses Readable, Navigable, and Editable.
Right, and it's a fascinating one.
Yeah, so here's the 60-second summary for you if you're building or managing agentic systems. The core problem is that modern AI agent harnesses are these massive, tightly coupled code bases organized by files.
Exactly, just folders and files.
Right, but when you ask an agent to modify them, you're asking for a change in behavior. And those two things just don't align.
They really don't. It's a huge disconnect.
So the solution they propose is this Harness Handbook, which is an automatically synthesized behavior-centric map of the code base.
Yeah.
It uses a workflow called Behavior-Guided Progressive Disclosure, or BGPD.
BGPD, yeah.
And it basically guides coding agents from high-level behaviors straight to the source code. The result, weaker models like DeepSeek V4 Pro can match GPT 5.5 in editing accuracy and actually reduce token usage by up to 12.7%.
Which is wild. I mean, better accuracy on weaker models for less money.
Right. So welcome to all the AI researchers and ML engineers tuning in. This deep dive is going to fundamentally change how you think about managing your agent architectures.
It really exposes this hidden assumption we have in machine learning right now. Like, we've spent the last 3 years obsessing over getting LLMs to generate better code.
Yeah, it's all about generation.
Exactly. But this paper proves that generation isn't really the bottleneck anymore. The bottleneck is localization. It's just figuring out where in this sprawling system a specific behavior actually lives.
Right, so let's diagnose that pain point. Because if you've ever tried to get an LLM to refactor a massive code base, you know how incredibly frustrating this is.
Oh, absolutely.
Let's start with the agent harness itself. Because, for anyone listening who just builds simple API wrappers, a harness is a much heavier piece of infrastructure.
Yeah, it's essentially the entire runtime environment that surrounds your foundation model.
The scaffolding.
Right. The foundation model just predicts tokens, right? The harness constructs the multi-term prompts, it manages the persistent memory, it decides when to invoke external tools, and it coordinates the execution loops.
It's like the engine block.
Yeah, exactly.
The LLM is just the spark plug. But the harness is the transmission, the fuel injection, everything that actually makes the car drive.
And because it's so complex, it's constantly evolving. Like, a product manager wants a new capability, or you need to tweak how an agent stops looping on an error.
Which brings us to the localization problem.
Right. Say you give an AI coding agent a request like, mask user secrets before writing the session recording to the log.
Okay, a behavioral request.
Exactly. But to actually execute it, the agent has to find all the code locations that implement logging, secret handling, and session management.
And in a real production code base, those aren't sitting in a neat little file called secretmasking.py.
I wish. No, they are completely scattered. You've got logic in the network module, something in the database schema, maybe a fallback error handler somewhere else.
A single behavior spanning hundreds of functions.
Exactly. The conflict is that human intent is behavioral, but repositories are structural. They're organized by where things live, not what they do.
Okay, but I have to push back here. Because if you're an ML engineer listening, you're probably yelling at your phone, wait, we already solved this.
I hear that a lot, yeah.
Right. We have semantic code search, RAG pipelines, massive 2 million token context windows. Shouldn't a frontier model just ingest the repo map or search for secret and figure it out?
It's a totally fair question. But if you look under the hood, those existing tools only make the code base easier to inspect. They don't bridge the semantic gap.
How so?
Well, if you use vector search for secret, you are still relying on keyword proximity based on the text of the implementation.
Oh, so Art might pull 5 different files that mention secret, but it doesn't explain the causal relationship between them.
Precisely. It leaves the coding agent to mentally stitch together how those isolated snippets interact. It doesn't tell you the execution sequence.
And what about just dumping the whole repo into the context window?
You're basically forcing the model to play Where's Waldo in a 2 million token haystack. The attention mechanism degrades. It routinely overlooks rarely executed code paths, like those fallback handlers you mentioned, because they just get drowned out by the noise.
Wow. Okay, so Tencent researchers realized we don't need a better search algorithm.
No, not at all.
We need an entirely different way of indexing code. A map that organizes knowledge by what the system does and then links that to the source code.
And that is the Harness Handbook. It's a behavioral index. It uses a very specific 3-level hierarchy to manage all this complexity.
Okay, let's walk through that. Level 1 is the system overview.
Right.
It's the 30,000-foot view, no code yet, just the overarching goals, architecture, and major lifecycle stages of the harness.
Then you drop down a layer to level 2, the component overview. This focuses on the specific working units within those level 1 stages.
Like what they do.
Yeah, their roles, inputs, outputs, and most importantly, how they interact with other components.
Got it. And then the ground floor is level 3, the unit deep dive.
Exactly. This is highly specific. Internal logic, state transitions, edge cases, all tied directly to function names and line numbers in the repo.
So it's basically Google Maps.
That's a great way to think about it.
A standard repo is just a raw database of GPS coordinates. Technically comprehensive, but totally useless if you don't know the route.
Right, you wouldn't just read a list of coordinates.
Yeah. But the Harness Handbook is the turn-by-turn navigation. Level 1 is the country map, level 2 is the city and highways, and level 3 is street view, where you see the front door.
Exactly. You don't load the whole country's addresses into memory when you just want to know which state to drive to.
Okay, but here's the obvious trap. How do you build this? Because if humans have to write this 500-page hierarchical blueprint, it's going to be outdated by Tuesday afternoon when someone merges a PR.
Manual is impossible, which is why the Tencent team completely automated the synthesis of the handbook. But they didn't just ask an LLM to read the code and hallucinate a manual.
Thank goodness.
Yeah, they built it in 3 phases to keep it factually grounded. Phase I is entirely deterministic static program analysis.
I want to really highlight this for you listening. There are 0 LLM hallucinations in Phase 1. None.
None. They treat the code base like a compiler would. They parse the raw text, extract an abstract syntax tree, and build a deterministic program graph.
So it knows exactly what calls what.
Exactly. Function names, files, signatures, line ranges. And if a call can't be statically resolved, like a dynamic invocation, they just log it as unresolved. They do not guess.
So you get this ironclad, ground truth skeleton of the software. Every bone is physically connected.
Right. Then phase 2 brings in the LLMs for behavioral structuring.
Adding the semantic muscle to the skeleton.
Exactly. But the prompt engineering is highly constrained. The LLM has to write plain language descriptions focusing purely on the why and the what.
Like, what problem does this block solve? What breaks if we remove it?
Yeah, it's translating raw structural graphs into human intent. And then phase 3 synthesizes the static graph and the LLM descriptions into that navigable L1, L2, L3 tree.
Okay, so we have this beautiful map. But if an AI agent just dumps the entire handbook into its context window, aren't we back to the needle in a haystack problem?
We would be, yeah.
How does the agent use this without blowing up its context?
This is where their runtime methodology comes in. It's called Behavior-Guided Progressive Disclosure, or BGPD. It dictates how the agent navigates from a high-level request down to the code.
Walk me through that. Let's use the mass user secrets example again. The agent doesn't even look at source code yet, right?
Correct. Source code is completely out of context. The agent only reads level 1 and 2 of the handbook. It finds the execution stages relevant to session recording and secret handling.
It's zooming into the city, finding the logging neighborhood.
Exactly. Once it finds the relevant level 2 components, it follows handbook links to include any other stages coupled through shared state.
Because a secret might be generated in the network module, but masked in logging.
Exactly. The handbook tracks that state transition, so the agent pulls in both. Then, only then, does it drill down to level 3 to get the actual source code locators.
But it doesn't just rely on the predefined links, does it? The BGPD workflow lets it expand dynamically using the call graph.
Yeah, 2 expansion modes. Function call graph or file call graph. If the masking function calls an external hashing library, the agent sees that and pulls it into scope.
Which leads to what I think is the most critical safeguard in the whole paper, source verification.
Oh, it's the anchor of the whole system. Up to now, the agent is just navigating the handbook, building a list of candidate locations.
Like 5 files and specific line ranges.
Right, but it does not blindly trust the handbook to write the edit plan.
Because the map is not the territory.
Exactly. The agent takes those locators, opens the live repository, and reads the actual source code snippets to verify if they are genuinely relevant. It only keeps the verified sites.
Wow. So by separating the search phase, which uses the dense handbook, from the edit phase, which uses verified source excerpts, it totally sidesteps the context limit.
Completely. You aren't forcing it to read 10,000 files to find 3. You give it an index that tells it which 3 to read.
Okay, the theory is elegant, but let's get into the benchmarks. Because ML engineers need to see the proof.
Oh, the proof is definitely there.
They tested this on real modification requests from Codex and Terminus 2, right? not synthetic toy problems.
Real complex behavioral modifications. They took a weaker planner model, DeepSeek V4 Pro, and ran it with standard tools, then with the Harness Handbook and BGPD.
And they benchmarked it against massive frontier models like GPT 5.5 and Opus 4.8.
And the DeepSeek model didn't just get a little bump. It matched or outright beat the localization accuracy of the massive models. Recall, precision, F1 scores all went up.
And the fact that recall and precision both increased is huge. Because usually a model gains the recall metric by returning like 50 wrong files just to get the right one.
Yeah, exactly, just an unfocused list. But because of progressive disclosure and verification, it pinpointed the correct locations without all that noise.
The win rates are staggering. Up 10 points on codecs across localization, scope control, and reasoning. And on Terminus 2, up 18.9 points.
But the real flex is on what they call search hostile requests.
Yes. Explain that, because it exposes the exact flaw in keyword matching.
Search hostile requests are when the implementation sites hide in fallback mechanisms or cold execution paths. If a user's request doesn't share vocabulary with the fallback handler, standard search will never find it.
Because the developer named the variable failsafe trigger instead of error try already misses it completely.
Right. But the handbook knows that failsafe trigger is causally linked to the retry behavior.
So on those search hostile requests in Terminus 2, the win rate jumped by 33.3 points.
It's massive. And similar gains on cross-file requests, where a capability spans a database schema, an API, and the UI.
Okay, but this brings me to a mathematical paradox. We're giving the agent this multi-level handbook. We're asking it to navigate L1, L2, L3, and verify against source code. Doesn't token usage go through the roof? The paper claims they used fewer tokens.
It seems counterintuitive, right? But it comes down to the token cost of blind exploration.
Right.
In a baseline run, an agent uses trial and error. It opens agent.py, eats 2,000 tokens, realizes it's wrong, and discards it. Then memory manager.py eats 3,000 tokens, discards it. It's just token slop.
It's like paying a cab driver to drive up and down every street looking for a house.
Exactly. But the handbook is highly dense. It might cost a few hundred tokens to read L1 and L2, but those summaries point directly to line 42 in utils.py. The agent bypasses the trial and error completely.
It just loads the 50 lines it actually needs.
Yep. So the final tally, 12.7% fewer tokens on codecs and 8.6% fewer on Terminus 2.
That is profound. You match GPT 5.5 performance and drop inference costs by 10% just by providing a better map.
It's a huge win for efficiency.
But I'm sold on the utility. Yet any software engineer knows the dark truth about documentation.
It rots.
The second a PR is merged, it rots. If someone refactors logging and moves functions, the line numbers in our beautiful handbook are wrong. Does this system require burning compute to regenerate the whole map every time you push code?
If it did, no one would use it in production. So the Tencent researchers included automatic resynchronization.
Okay, how does it stay fresh without hallucinating?
It leans on the deterministic foundation from Phase I. Every non-empty diff triggers an update, but it doesn't rebuild from scratch. It only updates the affected parts.
Oh, so just rerun static parsing on the changed files.
Exactly. Rehashes the syntax trees, updates the graph, and rolls forward the line numbers deterministically.
So if I move a function down 20 lines, the parser physically sees it. The LLM isn't guessing where it went.
Right. The LLM is strictly confined. It's only used to classify the diff and revise the plain language description if needed. The structural mapping is entirely static facts.
What if a developer pushes total garbage code? Like they mangle a function signature so badly it can't parse, or the LLM can't classify it. Does the system confidently guess and corrupt the handbook?
They built a brilliant fallback for that. It handles unparsable content with extreme conservatism. It freezes it.
It freezes it.
Yeah, it records it as a coverage gap. It basically leaves a marker saying, this section changed, but I cannot resolve its behavior right now.
It prefers to be incomplete rather than confidently wrong.
Which you absolutely need for an operational tool. By limiting LLM inference during the resync, the Harness Handbook maintains its authority. It stays a living blueprint that you can actually trust.
Well, let's summarize the mission of this deep dive for everyone listening. As we move toward fully automated software engineering, we're finding out that writing the code is actually the easy part.
The easiest part, yeah.
The true barrier is behavior localization. It's bridging that massive gap between what a human wants the system to do and where the sprawling files actually implement it.
And the Harness Handbook proves that when you bridge that gap by abstracting implementation into behavior, you unlock incredible efficiency. Weaker models punch way above their weight, accuracy spikes on cross-file edits, and you eliminate all that wasted exploratory token slop.
It is a fundamentally new paradigm for interfacing with complex software,
It really is.
which leaves you with a slightly provocative thought to ponder. If AI coding agents can now seamlessly translate natural language behaviors into exact code-based coordinates, and if these dynamic handbooks are constantly updated to reflect the live system perfectly, are we rapidly approaching a threshold where human developers will no longer need to read raw source code at all?
That's the real question.
Right. If you can interact exclusively with a behavior-centric map, will we eventually just leave the messy structural file systems entirely to the machines? Something to think about the next time you're lost in a massive repo. Until next time.